second solstice of the Stanford University Mathematics Society. And thank you for coming. We did have actually several people actually coming, so this is good. And our present, our lecturer today, our speaker today will be Professor Touchette from the Applied Mathematics Department. He's a professor at and professor of applied mathematics. And just a bit of background. So he got his PhD at Montreal University in 2004. And then he did his postdoctorate and he's lecturing at the Queen Mary University of London from 2004 to 2013. And now he's also doing he started lecturing at Stellenbosch from 2013 already. So it's quite a long time for that. And today he will be speaking about predicting and simulating reweighings. So I hope you enjoy it.
Thank you, Daniel. Thank you for the invitation. Thank you for coming in such numbers. It's good. I've asked Daniel to be in this room because we have proper blackboards here. I'm surprised to see that you guys and your maths don't have proper blackboards. And I thought I won't force you to cross the road to come over to applied mathematics, so then there's the middle ground. Okay, so the idea for this talk is I don't need to reach a goal in the talk. I have some slides, I have some material, but the goal is to give you an idea of the research that I do in what we call large deviation theory, which is a subfield of probability theory, and it deals with rare events. So I want to give you an idea of what a rare event is, how we can estimate probabilities for rare events, what kind of rare events we can deal with or encounter in life, and why they're important in applied mathematics or in physics. So my background is actually physics, but I was able to sneak in to become someone in applied maths. In the process, I think I became more of a mathematician, but that's not for me to say. Okay, so a rare event just simply is something as an event that has a small probability. And then the question is, how small is small? And it really depends on the application and the kind of systems that you consider. So here I give some examples like gene mutations. I think you know when viruses reproduce themselves. So when you have cells reproducing themselves in the coding of the genetic information, there might be some errors in the transcription. So in the RNA transcription, there might be some errors introduced. And then you have very small probabilities of the errors. Actually, cells, when they reproduce quite faithfully. But there could be some errors, we call these mutations, and the probability of a mutation is very small. It depends on the cell or virus that you consider, but it's considered a rare event. Then you have protein configuration change. So I think you know you have different proteins in the body, and then the function of the protein is determined by the shape that it has in space, and then you can have change in the shape, and these changes are produced by thermal fluctuations. And in chemistry, you would describe this as a kind of two valleys, and then you have a configuration that's stable, and then you need some noise, some perturbation to change the configuration to another stable configuration. And that transition is also rare. You have very small probabilities for this to happen, something like 10 to the minus 6, 10 to the minus 10 in terms of probability. So these, we're dealing with very small probabilities. And then you have many other rare events that you can consider, like tsunami, extreme weather, financial crash. So here I show the Lehman collapse, where an actual company actually closes because the stock is worth nothing, and so it just terminates. And then you see this is a kind of random process that evolves into a state that's very unlikely, or at least we thought at the time was unlikely, even impossible. And then the goal is to try to estimate what's the probability of that event, that kind of collapse or catastrophe. And then in population dynamics, you can see something similar there, where a population will collapse too, it will just get extinguished. And then this is also considered a rare event under some circumstances. And then you have other situations where you can envision events that will happen with a very slow probability in computer science and again in population dynamics. So it's quite general. You have a stochastic system, you have different events or different behaviors that can happen. You have typical behaviors, so typical behavior is what you expect with a high probability, and then you have rare events that are events with a very small probability. So anything down to 10 to the minus 2 down that is considered a rare event, and sometimes a rare event might be rare, but the effect of the event might be so big that you're interested in that event, so you want to estimate still the probability, even though the probability is very small. And then in some other cases, the event itself is very small, but because it's compounded many times, it becomes typical. And then an example is the gene mutation. The gene mutation by itself is very rare, but because viruses are so widespread, they have millions of viruses being reproduced at the same time over a long time, the probability to get a variant like the Omicron is actually not a rare event. So you can get variants of a virus happening with a high probability, even though the process driving the appearance of a variant is something very rare. Okay. And then you have the same also with the molecules. The change, the configuration change is very rare, but because the chemical reaction is always happening at microsecond scale, and then over some time, like a minute, actually you'll see that transition happening with high probability. Even though at the dynamical scale, at the chemistry scale, this is the rare. Okay, so this is to set the stage in a way, and the way that we're going to study this mathematically, the simplest case that you can imagine where you can make sense of these rare events is sums of random variables. And then I'll try to illustrate everything with the simplest case, even for sums of random variables, which is sums of independent random variables. Okay. And then I'll try to move on then to stochastic processes based on what I'll be presenting for sums of random variables, but the ideas that I'll be presenting are quite general, and then gives you an idea of what we're doing really for stochastic processes. So I'm not really working on sums of random variables. I'm working more in the situation where you have a stochastic process evolving in time, and then you want to define some rare event, or you're dealing with a rare event, and you want to estimate the probability of that rare event. So you need a dynamical model of the stochastic system, and then some method to estimate that probability. And then what I'll do again is consider a very simple case where you have a sum of random variables, and we'll try to define a rare event, and then I'll just present techniques to calculate estimated probability. And these techniques are the same techniques that we use for stochastic processes. Okay, so we're doing. Okay, so this is where we're using the one. I want to define that sum of random variable. This is really at the core of large deviation theory, that theory of rare events, because it all started with sums of random variables. So what we have is what we call a sample mean. So we have a sum, but it's divided by the number of random variables that we use. So we call this a sample mean. This is like if you want to estimate the mean of some population, this is your estimator. It has some nice properties. And this simple case I'll consider is the case where you have ID random variables, meaning independent, and they all have the same distribution. So this means that if you consider the probability distribution for the n of n, it's the product, you have the independence property. Like this, and the distribution for each of them is the same. So you could look, for instance, at the sum of Gaussian random variable, and they all have the same mean and the same variance, or sum of exponential, and so on. And then the goal is to calculate the probability distribution of the sum given the model. So given the ID model, given the distribution for each of the random variables. If you have discrete random variable, the sum will be discrete. If you have continuous random variable, the sum will be continuous. So the distribution will be a discrete distribution or a continuous distribution, but I'm not going to make a distinction between the two. I don't want to consider the two cases with different notation. So I'm just going to write something in a sloppy way, something like this. So this is, I want the distribution, so it could be the density for a continuous random variable or discrete distribution for a discrete random variable. And I just want the distribution for the sample. So we don't get to teach this in the first course of probability theory that I teach in first year. It's something actually that you don't even get to see, I think, as an undergraduate, but it's a very interesting problem. And then it shows up in many things, and the context where it all started is the context of insurance. So that sum is a sum of claims that an insurance company will receive. And so the insurance company has to know what's the distribution of the sum of claims because it needs to set the price of a premium. of an insurance to cover for the potential losses coming from the claims. So it started in the 30s in actual science and trying to determine distributions of sums of random variables. And the current technique at the time was to approximate everything as a Gaussian. So you say the sum will be Gaussian, that's the central limit theorem, but then it's not very good for insurance companies, and I'll mention why later. We'll see why actually the Gaussian approximation is not good. Okay, so how do we get the distribution of the sum mathematically? Anyone knows except you one actually works on this? How do you get the distribution of a sum of random variable given the distribution of the random variables that you sum? How do you get that? Okay, so there are two basic techniques for this. One is it's a convolution of the basic distribution for the random variable, and the other one is the Fourier transform, and that's suggested from the fact that it's a convolution. So the first result that we have is that the distribution, and I'm going to write this just like in abstract form, is the convolution n times of the basic distribution. And then we're going to have, at the end, the convolution is expressed as a function of that variable s, which is the values, the possible values for this. Okay, so this is an identical convolution. Convolution is something that people use a lot in engineering when they look at image processing or signal analysis. So this shows that it's not going to be so easy because you need to calculate a convolution n times. So then there's another suggestion, which is if you take the Fourier transform of a product of a convolution, it's the product of the Fourier transform. So you could also write a distribution as the inverse Fourier transform of the Fourier transform of the distribution that you raise to the power n times. And then as you do the inverse Fourier transform, it will be expressed as a function of that variable s for the values. Okay, so you have two ways to calculate this. The Fourier transform obviously is easier because everything then is a multiplication. So the goal is to have the Fourier transform, you take the Fourier transform of the distribution, you take the product n times, and then you take the inverse Fourier. But in general, that's quite complicated. Okay, so there's a theory behind this that says that actually distribution will have a general form. So there's no need to try to compute this exactly. There's a general form that's easier to calculate. And that's the basis of computation. So I'll show you two examples to try to justify where this is coming from. We'll take first a sum of Bernoulli random variables. So you've all taken probability theory statistics 114. Who was in my class? Okay, good. First example. Sum of Bernoulli random variables. So I have a sum of random variables, sample mean, and then I have a sum of xi's, and Bernoulli means that the xi's have the values zeros and ones. So you're just summing random bits. And then I'll take a simple case where the probability for the 1 is 1/2. And that's also the probability for one of the random variables to be 0. Okay, so just balance Bernoulli. And then I take the sum of the random variable, and now I'm asking, what is the distribution of the sum? And this is something we've seen in 114, but not in that form. What is the distribution of the sum of Bernoulli? Anyone can tell?
Binomial.
Binomial. Okay, so this one, I know the distribution exactly. I don't need to go over the Fourier transform. And so I can write directly that the distribution of the sum here is actually 1 over 2n, and then I have the combinatorial factor, which is n factorial, and here I'm going to have the fractions of 1s, so it's n times s, and then here I'm going to have 1 minus s n, this. Okay, so that's the exact distribution. It's good. This is what I want to get, but I want to calculate the distribution for a very large n. That's the goal. And so here you can use what we call the Stirling approximation for approximating the factorial, and what you'll get to dominant order. So the dominant part will be something that decays exponentially. That's really the crux of where I want to go to. The distribution goes down exponentially with n, and there's a certain function that we're going to call the rate function. And that rate function here is log 2 plus s log s plus 1 minus s log 1 minus s. And it has that shape. 0, 1. So the sample mean will be 0 between 0 and 1 because you're summing 0, 1 random variables, and then you divide by n. And the rate function looks like this. This is IS. Now, if you look at this and you look at this result, you see that the distribution will be biggest, largest, where the rate function, that function is minimum. And this is at 1 half. And this makes sense because if you take the sum of 0, 1s that are actually balanced, then the most probable value of the sum is 1 half. And what this says is that any other values away from 1 half is exponentially unlikely, so that's the rare event. Okay, so here we have a very precise form of rare event where the probability is exponentially small with n. Okay, so that's our first example of rare event. Let's take another one. Another one will be a sum of Gaussians. This is also easy because I know the distribution is also Gaussian. So I don't need to compute the Fourier transform or put more convolution. Yes?
Is it an accident that the IS function looks a lot like the Shannon entropy?
No, and we'll come to this.
Okay.
Okay? So let's take the case where the random variables are all Gaussians with the mean mu and then the variance sigma squared. In this case, I know that the sum of Gaussian is Gaussian, so I only need to compute the mean and the variance, and I'm going to square the detail. The full distribution, the exact distribution, is something like this. Okay, now I look at this in terms of n behavior. I see the decaying exponential, and then I see the n at the front. The n at the front is really self-dominant. It's not even important. It's like a normalization. Right? If I plot this as a function of n, what dominates the whole thing is the decaying exponential. So I can say, I'm going to approximate this again, and I see this form here and again, decaying exponential. The only difference here is the rate function is different. The rate function is parabola centered at the mean. So I plug this. The rate function is this. It's positive, it has a 0 at the mean. The curvature will be determined by the variance. And then I read this with this result. What is the most likely value of the sample mean? It's the mean. So everything will concentrate at the mean. And everything else away from the mean is exponentially unlikely to happen. So again, rare. So I could calculate, for instance, the probability that the sample mean is greater than the mean plus epsilon, which means that I would look at all this probability coming here. This also will have to be exponentially small with n. So I have a rare event. Okay? That's rare again in the exponential sense. So you see where this is going. I have two examples where I have this nice form, this decaying exponential. There's an approximation there, and then we'll see what this means. But the upshot is that if you take undersample means, you'll still see that decaying exponential. And then you can calculate the rate function. That's the goal of the theory, is to get that rate function. And to calculate that rate function, you don't need to calculate the Fourier transform. You don't need to calculate the convolution. And so it's simple. And it shows up also in other contexts where you're not dealing with ID and variable. And this is what I want to say. Okay, so the first result where this exponential approximation actually came up is a result by Marat Gamer in 1938. And he was the one working on insurance statistics. So the sample mean for him was the sum of insurance claims, and then he wanted to calculate the distribution for the sample mean going beyond the central limit theorem, so not approximating the whole thing as a Gaussian. This is what people were doing before. And the reason why it's not good is because if you look at the Gaussian approximation, you might undervalue actually the underestimate the probabilities, and so you're making an error as an insurance company as to how likely claims can be, and so you're going to lose money. So you need, at that time, they just needed a better approximation of the density, and this is what you come up with. The exact density, and this is a nice result, the exact density will have that exponentially decaying factor, and then a whole lot of corrections, but they're all subdominant compared to the exponential. Moreover, the rate function, this is what I call the rate function, that I of S function, which describes how likely the values of the sample means are, is given by some kind of what we call a Legendre transform. Here is the Legendre transform of the cumulative. Okay? And this is, I'll get to this in a second as to why this is. So if you want to describe the distribution, then you need to calculate that rate function, this I of S. And in order to do this, you need to calculate the cumulative of the distribution and then take the Legendre transform. So then you just boil down problem and probability theory to a problem in analysis. So this is the starting point of the theory. It took a long time. I'm not doing the history of the subject, but the first result is 1938, and then the theory emerged in 1960. Okay, so there's quite a bit of time before people realize that it's something general. And then they realized that this exponential approximation actually arises in many contexts, including Markov processes, and so they made a theory out of this. And the basic definition of that theory is that exponential approximation. That's the starting point of everything. So this is, I'm just summarizing now in one slide what the theory is about. You have a random variable. It's actually a family of random variables. It's a collection of random variables. So it could be something like a sample mean, but it doesn't have to be a sample mean. It could be a product of random variable. It could be, in physics, the energy of n particles. It could be many things. What's important is that you have a random variable that's indexed by some parameter. That's the n. Okay, so that defines a collection of random variables. And the n at some point will let n go to infinity. We want the parameter to be large. We want asymptotics in the limit when n goes to infinity. We're interested in calculating the probability distribution. That's what we're after. And then we're expecting that distribution to have this exponentially decaying form. And so we give it a name. It's called the large deviation principle, or the large deviation approximation. And here I'm putting the meaning of the wiggle sign that we use all the time in physics to express approximation. It's an approximation in what sense? Here I've used in terms of language is the dominant part of the distribution is the exponential. How do you make sense of this? Well, if you take the log of the distribution, it means that the main part will be linear in n. That's the main part that we have. Then anything that comes after in terms of corrections will be smaller than linear in n. And then in maths and computer science, we use the small notation to express it. So you have, if you take the log of the distribution, you get something that scales like n, and then corrections to that term that will scale smaller than n. So if you divide by n and take the limit, what you see is that you just retain the rate function. And I can do this with this. If I take the log 1 over n and take a limit, I'm going to kill this term, and I'm going to retain only the product. If I do the same thing for the sum of the new mean, I'm going to do the same thing. So this is the limit that defines the rate function. So we say that the distribution satisfies the large deviation approximation, or the large deviation principle, if this limit exists and defines a non-trivial function. So different from 0 everywhere, or different from infinity everywhere. If you have that limit, then you have this approximation. And the goal of large deviation theory is to, if you define your model, you define the random variable of interest, large deviation theory will give you techniques to show that you have a large deviation principle, and then another bunch of techniques to get the rate function behind this. It's all about this. And this will give you the mean to estimate the probability of the rare events that you have. And the reason why it's a theory is because, again, that exponential approximation arises in many cases, not just the sum of random variables. Okay, so how do you get this? So I'll show you just one result in the theory that's called the Gaussian theorem, which is this result. It gives you exactly what you want. So if you start with that random variable an, then you want to show that the distribution of an has this exponentially decaying form. You don't know the distribution. You don't want to calculate the distribution exactly to realize that it has this exponential form. Right? So for the two examples that we've done here, I was able to write the exact distribution to realize after that it has that dominant exponential form. But I don't want to do this. I want to be able to show that it has a decaying exponential form without calculating the exact distribution. Otherwise, it would be defeat the purpose completely. I want something that's simpler than calculating the exact distribution to get to the estimation of the longitude deviations. Okay, so the main result that we use is this one, Gardner-Ellis theorem. It's a very useful result because it goes beyond sums of random variables, and even it goes beyond ID sums. And the way that it does this is by considering another quantity, which is called the scale cumulative generating function. So it attacks the problem by just moving around a bit like you take Fourier transforms to calculate distribution. It just looks at some different quantity. If you're able to calculate some properties about this quantity, then you can get the rate function from it. And this quantity is, to begin with, it's an expectation. So it's an exponential expectation of the random variable that you're interested in. The expectation of this form is called a generating function. If I take the node, it's called a cumulative function. If I put an n here and I put the limit, we call this the scale cumulative generating function. And then we denote this by lambda. So it's a function of k. The k here is a real quantity. It's a bit like taking Fourier transform. In fact, it's a Laplace transform of the distribution. And so the theorem says that if you can calculate this scale cumulative generating function without knowing the distribution, I'll show you can do this. And then the function is differentiable, then you have an LDP, so it means that the distribution of the random variable does decay exponentially with the number n, with the parameter n, and the rate function is just like in Cramer's theorem, it's a Legendre transform of the lambda k. So you calculate this lambda k, and then from lambda k you can extract the rate function, that's the rate function that you have. And it's quite a useful result. We also see Legendre transform in thermodynamics. It appears in physics. In fact, it appears also in mechanics. The Newtonian is the Legendre transform of the Lagrangian in classical mechanics. Okay? And it appears in that context for similar reasons. So what I want to show you now is that this Gardner-Ellis theorem actually, I'm not even specifying what AN is, right? It can be a sum, it can be a product. It doesn't have to involve independent random variables. It's anything. As long as you can calculate lambda k, you're in business. But if you take as a particular case the sum of ID random variable, then the Gardner-Ellis theorem reduces to prime. Okay, and the result is not so difficult because what you have here for a non-ID sum is the log of the expectation of k and then a sum. So what you do is that expectation of a sum is the product of the expectation. If you're dealing with an independent random variable, the expectation of the product is the product of the expectation. Okay, so for ID random variable, what I'm going to have here is 1 over n, and I'm going to have the product of expectation for the k is I. The log of the product is the sum of the logs, and then they're identically distributed. So this expectation is the same for every I. So at the end, the limit disappears, and I get a single expectation for a single random variable. They're all the same, they're all identically distributed, so the cumulative is the same for each of the random variable, and so this is one. So for ID sample mean, the Gardner-Ellis theorem actually reduces to Cramer because now you see the rate function is obtained by the Legendre transform of the simple cumulative of one random variable, which is what Cramer had in 1938. That result of Gardner-Ellis is 1980. Now you can play the game now. You can take your favorite random variable as a sum, and then you can play this game. Without knowing what's the exact distribution, you can get the large deviation approximation. For instance, if I start again like I did as a sum of Gaussian, I can calculate lambda k. The cumulative of a Gaussian is a parabola. The Legendre transform of a parabola is another parabola. And if you do the full calculation, you get the function I showed you before, that I got from the exact distribution. Here I'm not calculating any exact distribution. I get the exponential approximation as a two-line calculation. Back of the input, very easy. A more difficult example is take a sum of exponential random variable. Then we don't know what the exact distribution